Our topic today is intermediate value theorem and squeeze theorem and their relation with more continuity. Here's the content. First, we will introduce the objectives of this class. Second, we will state the properties of continuity. Third, we will discover the intermediate value theorem and do some practice. And then we will go to the squeeze theorem with more practice. Lastly, we will talk about the homework. The objectives of this class is to understand and use the intermediate value theorem, understand the squeeze theorem, and use properties of continuity to make an interval continuous. Properties of continuity. If the function f and g are continuous at x equal to c, then the following functions are also continuous at c. The first one is scalar multiple. The second is sum and difference. The third is the product. The fourth is the quotient. And the last is the composition of two functions. Intermediate value theorem state that if f is continuous on the closed interval a and b, and k is any number between f of a and f of b, then there is at least one number c within a and b such that f of c equals to k. Here's the representation that states the intermediate value theorem. You can see in the two graphs for both a and b, there must be values that equal to w that between them. Let's look at the first example. Verify the intermediate value theorem applies to the indicated interval and find the value of c guaranteed by the theorem. F of x equal to x squared minus 6x plus 8. In 0 to 3, find f of c that equals to 0. First, we plug in the numbers to the function and we can get f of 0 equal to 8 and f of 3 equal to -1. Then we copy down the intermediate value theorem. If f is continuous on the closed interval 0 to 3, and k is any number between -1 to 0 to 8, then there's at least one number c in the closed interval 0 to 3, where f of c equal to 0 by the intermediate value theorem. We will verify this by make the function equal to 0. And then we simplify both parts, so we can get x of equal to 4 or x equal to 2 has a solution of that equal to 0. And x equal to 2 is between 0 to 3, so c is 2. So why do we care about the intermediate value theorem? If we know that a function is continuous and this function has positive values of f of x and negative values of f of x, then we can conclude that somewhere f of x equal to 0. Stated that if h of x less or equal to f of x less or equal to g of x for all x in an open interval containing c, except possible at c itself, and if limit of x to c of h of x equal to L equals to the limit of x to c of g of x, then the limit of x to c of f of x exists and equal to L. And this is the graph represent this theorem. As you can see, hx, fx, and gx are equal at point C. Let's see an example. Firstly, I want to give you the tips for making piecewise functions continuous. For a piecewise function to be continuous, each function must be continuous on its specified interval, and the limit of the endpoints of each interval must be equal. Okay, let's look at an example. What value of k will make the given piecewise function f of x continuous? Firstly, we state them to equal. So, if f of pi equals to sine of 2 pi, then f of pi equals to 0. And we put the limit x to pi, 2x plus k equals to 2 plus k. 2 pi plus k equals to 0, then k equals to negative 2 pi.
The first question is piecewise function of f of x equal to 3x squared, x larger than or equal to 1, and ax minus 4, x less than 1. And we first replace x into the first function, and it's equal to 3. Limit x to the negative 1. Ax minus 4 equals a minus 4. And we can know that a minus 4 equals 3. Then a is equal to 7. The second question is the piecewise function of f of x cubed. X is less than or equal to 2. And ax squared, x is larger than 2. We first replace x into the first function, and it's equal to 8. The limit x to the positive 2 ax squared is equal to 4a. And 4a is equal to 8. A is equal to 2, and it's the final answer. The third question is the piecewise function of f of x equal to 2, x is less than or equal to negative 1. F of x is equal to ax plus b. Negative 1 is less than x and less than 3. F of x is equal to negative 2 when x is larger than or equal to 3. And we can get when x is equal to 3, f of x equal to negative 2, and the limit of x to the negative 3, ax plus b is equal to 3a plus b. Then 3a plus b is negative 2. When x is equal to negative 1, f of x is equal to 2. The limit x to the negative 1 from right, ax plus b is equal to negative a plus b. So negative a plus b is equal to 2, and b is equal to 2 plus a. And we can get 3a plus 2 plus a is equal to negative 2 and a is equal to negative 1. b is equal to 2 plus minus 1 and b is equal to 1. f of x equal to x squared and g of x is equal to x minus 1. H of x is equal to f of g of x and h of x is equal to the square of x minus 1. So it can be interpreted that h of x is everywhere continuous because f of x and g of x are both everywhere continuous. The fifth question is f of x equal to 1 over x minus 6 and g of x is equal to x squared plus 5. H of x is equal to f of g of x and h of x is equal to 1 over x squared plus 5 minus 6. So h of x is equal to 1 over x squared minus 1. So h of x is continuous everywhere except x is equal to negative 1 and x equal to 1. Question is f of 1 is equal to 37 over 12 and f of x is equal to negative 8 over 3. So f of x is continuous on the closed interval 1 to 2 with one value being positive and other being negative. But because of the intermediate value theorem, there must exist a zero between the 2 points. The seventh question is f of x is equal to x squared plus x minus 1. F of 0 is equal to negative 1 and f of 5 is equal to 29. Since f of x is continuous on the closed interval 0 to 5 and negative 1 is less or equal to 11 and less or equal to 29, there exists a value c, 0 less or equal to c and less or equal to 5, where f of c is 11 by the intermediate value theorem. So 11 is equal to x squared plus x minus 1 and x is equal to 3. F of x is equal to x squared plus x over x minus 1. F of 5 over 2 is equal to 5.83, where 3 is the circulating decimal. And f of 4 is equal to 6.6, where 6 is the circulating decimal. So f of x is continuous on the closed interval 5 over 2 to 5 and 5.83, where 3 is the circulating decimal, less or equal to 11 and less or equal to 6.6, where 6 is the circulating decimal. Thus, there exists a value c, where 5 over 2 less or equal to c, and c less or equal to 4. Such f of c is equal to 6 by the intermediate value theorem. And 6 is equal to x squared plus x over x minus 1. So x is equal to 3. The next question is f plus g is always continuous, and f over g will not be continuous where g is equal to 0. Because when g is equal to 0, f of x is equal to x squared plus 1, and g of x is equal to x minus 1.